everyone, and welcome to the Climate Emergency Forum programming that is in concert with the Facing Future. Hello, everyone, and welcome to MEER Reflection Framework, a program brought to you by the Climate Emergency Forum in collaboration with Facing Future. So, it's almost a dirty word, geoengineering. When people hear it, there's a reflexive reaction. It's very fear-inducing. You have the mad scientist effect kicks in. It's, well, things are bad now. What are they going to do that's going to make the situation worse? But one of the things that I've heard, and I believe it might have been compliments of Mr. Tao, is we are already engaged in a geoengineering experiment, and that is we are pumping CO2 into the atmosphere day after day, year after year, and we see how that has turned out. And unless we do something and we continue to do the same thing, we know that we are headed towards our own demise. And so we're looking to the best and the brightest to help solve this crisis that we've gotten ourselves into. And we have Dr. Yi Tao here with us today to discuss with us the MEER Reflection Framework and perhaps provide us with a degree of hope of what we can look for in the future. Can you share some of your thoughts with us?
Yes, please. So for those of you who are watching offline, it's important to follow this talk by looking at the slides. You will find that on the website afterwards. So I'd like to thank the host city, Glasgow, for hosting all the climate conference, and also it's been an inconvenience for many, including the students, who are protesting the closure of their dorms, and also the human hotel hosts who are hosting many of us here. So it's an honor to speak after the youth, both the students in the session before and also the youth climate activists. And MEER Reflection, our central aim is to empower the youth, to empower the underprivileged, using century-old wisdom that our forefathers and indigenous communities have given us. So you see there some designs of simple banners that are reflective. And if, let's say, let's go a bit forward. If Greta Thunberg and her many followers were to use these reflective banners on their Friday strike, they can together offset 1 megaton of CO2. And today we'll look into how that's possible. But in order to understand, we have to, unfortunately, talk a little bit about the core principles of global warming in a mini lecture. We'll then be able to understand why, for example, fixating on CO2 will not lead to success. And that actually, if we take another perspective, from the energy flow perspective, we're also overpowered by the problem by a factor of 100 to 1 at least. So it's a very dire situation. So we need to really use out-of-box thinking and just look at the problem from multi-dimensional, different perspective in order to find a potential solution. And I'd like to end with a note of hope, a rational hope, that's based on experimental data and a very careful analysis. So we know that we are on a trajectory of this Earth starship that's bringing us towards environmental catastrophe and ecological degradation. And we recently have learned that actually what we do in terms of mitigation and the greenhouse gas emissions in the next 2 decades or so will have very minimal impact on the trajectory. So essentially, it's almost guaranteed that we'll be surpassing the 2-degree threshold within the next 20 years to 30 years. So now let's step back and look at how the universe functions. There's essentially like 3 components at the core. There's material, there's energy that drive material transformations, and they evolve according to some physical laws, which also includes our social values and our technologies. So at the core, you can think of many things in this universe as nodes. For example, water in a funnel. So you have water coming in and going out. If you have more water coming in per unit of time than going out, then you will have an overflow of the, that's basically what's happening with the greenhouse gases. And if you have a faster depletion, then you're injecting or renewing the resource, then you have depletion. So that's what we're doing with many resources on Earth. So we can also conclude that a node is stable or society is sustainable if we can simultaneously balance all of those source and sink rates for all the different processes that's ongoing. It's a very grand challenge, but that's something we need to aim and work towards. So now you're ready to understand climate change in just one slide. Essentially, the two central core nodes are the collection of greenhouse gases, and there's the heat in Earth's biosphere. So we have increased the source rate for greenhouse gases, leading to a positive source minus sink for that node. And that leads to an increase of the size over time. Functionally, the coupling between the gas and the heat is such that that leads to a compression of the sink rate. And now we have a new imbalance, more heat coming in than going out. Then as a consequence, we have heating of the Earth as a function of time. But of course, that's only on the physical side. We also have the biosphere, of which we are a part. And that's the node that most immediately impacts us. And the interaction there is very similar. We have a shutting down of the source rate of biosphere production. So let's focus on that particular interaction for a second. So one can do a literature search and encourage many students and colleges to do that. If you look at the impact of different individual climate stressors on primary production, that is the growth of crops or phytoplankton, you will find that almost universally, high temperature perturbation will lead to deterioration in performance, so is the deprivation of water. In terms of flood, it's a little bit mixed, but temperature and the drought are real killers. They're so important that over the past 20 years or so, we have seen a reduction in total factor productivity of 20 to 30%. That's very dramatic. And it's especially a problem in regions where temperatures are above 30 degrees. So now we can discuss why it's too late to really focus on the source rate for atmospheric gases, and why it's infeasible practically to focus on the sink rate for that node on top. There's already too much CO2 and greenhouse gases in the atmosphere, and even if we stop the emission, we will most certainly be inching towards 2 degrees Celsius in the next 20 years or so. And if you think of the problem as removing this mass from the atmosphere, then you can see how much each of you, that little dot, that's your body mass, that you are responsible for removing in your lifetime. And it's a lot of carbon to remove. In comparison, the total amount of carbon that we can sequester in forests, both artificial and also rebuilding natural forests, are just a small fraction of what's needed to really combat this problem from this perspective. So let's say we were to do this industrially. And let's say that somehow we were to devote all of our energy to this process. Then each of us have about 2 kilowatts of thermal power to do so. And of course, if we were to use all the energy to do that, then somehow aliens have to give us the 10 million direct air capture plants in which we can do this process, and also feed us so that all of us can work like slaves 24/7 in order to capture carbon. So in the end, after a year, we would have captured back the energy that's used to generate, to power the process. In the end, we have done nothing. And of course, there's no aliens. We have to make the infrastructure, and it takes more energies than we have just to make the basis or some of the chemicals for the process. So in a sense, we need roughly about 10 years of current primary energy production to power 1 year, to capture 1 year of emissions. And of course, there's also material usage and environmental degradation, which often exceed how much you are using or capturing. So in summary, to capture CO2 industrially amounts to trying to do a very inefficient process, while as long as we're still powered by fossil fuel, basically burning a lot of fossil fuel in the process, and also sequestering that burning into the underground rocks. And basically, after 15 years, we would have managed to deplete all of our fossil fuel reserve by basically burning them and injecting them into ground, and in the process, doing nothing for atmospheric CO2 concentration. And if we were to do such a process, we would have generated so much heat that it itself would have an impact on warming. And of course, there's a lot of plastic generated in the process. So why does such a process get funding at all? That's because we're operating in a neoclassical economic system, and that anything that degrades the environment and powers just consumption of resource in this sort of wasteful cycle is encouraged. So now let's talk about addressing the heat node, which is potentially much more effective. So even here, it's a very stark challenge. So the heat balance, basically how much heat is coming in versus minus how much is going out, is roughly 400 to 1,000 terawatt. And that's like 50 times the energy that we have available, even powered by fossil fuels. So basically, we're trying to fight a monster which is much, much larger than the brute force fossil fuel power we have. In comparison, each of you have the power of a hairdryer, but each of you are responsible for an industrial scale heater that's 100 kilowatt. So we obviously need some kind of leverage in order to overcome this gigantic monster. And we do not really know what that leverage is yet, but hopefully you will learn how that's possible. And of course, we're talking about MEERs. And the idea goes like this. We have decreased the sink rate of heat from Earth through global warming. What if we just decreased the source rate proportionally? Then we can have the same steady state size for the amount of heat that's trapped in the atmosphere to first order. Okay, so here is something that actually is surprising and might help us. We know that climate change is inducing a lot of problems, extreme heat and extreme drought. And of course, that's first driven by high CO2 concentrations, which cause the heat and cause the drought, etc. But if we can somehow decouple that step, the CO2, the presence of CO2 from the heat generation, then we can essentially negate or attenuate to a larger degree downstream impacts. So in a sense, if we look at CO2 impact from a multidimensional, a multi-factor point of view, we can selectively target the heat while leaving some beneficial impacts, including fertilization of primary production and water use efficiency. So essentially, we know where to go, where to drive this spaceship Earth that we're on. We need to go back in temperature, and it doesn't really matter which way we go. We can even afford to really power the process by carefully using fossil fuel energy and tolerate slightly higher CO2 concentrations as long as we can lower the temperature. So the process turns out to be very affordable because glass is very cheap to make, both in dollar amounts and in energy amounts. So to cancel 1 ton of CO2 warming, we basically need about $1 to $10 of investment in energy and in finances. So essentially, we can basically start to cool Earth beyond the 2040s if we just devoted on the order of $500 billion US per year to build such infrastructure, which would protect against agriculture. And in agriculture field, right now, we're basically losing $500 billion per year. And there are many other impacts coming down the line that are much, much larger in cost. So we have estimated how much energy can be rejected, really, by these MEERs on the ground. The process is somewhat involved because light comes in at very different directions, depending on the climatic conditions and your weather conditions, as you see in the 2 different MEERs. So that's an image showing on the x-axis the direction of the light traveling around in azimuthal axis, and on the y-axis, the polar axis. It's mostly coming down. And when we calculate the reflected light, we get about 70 to 80% going back through the atmosphere. So it's effective. And we can also estimate efficiency as a function of location on Earth, and pretty much we have on the order of 100 to 150 watt local radiative heating, cooling. So here is how we have that leverage to overcome the climate monster. So we make MEERs using your very limited thermal power. You put it outside, and in 4 days, it would have rejected enough thermal energy that went into its fabrication. In a month, it's already much larger. In a year, you would have overcome the climate monster. And in 3 years, it's drastically larger. So basically, what gives MEERs this leverage is that once you make it to high standard, it will be sitting there passively and doing the work for you, as long as you don't break it by vandalism, for example. So we need to return to timeless values that honors quality and durability in products, and we really should criminalize planned obsolescence. So here's another view to make it more intuitive. To cool your house, you need to have a constant input of electricity and a constant output of heat from your house. But in the case of MEERs, basically you have, you make it once, then it will be sitting there accumulating benefit. All right, in the last few minutes, I'd like to show some preliminary data. So that's a plot of the power of the amount of sunlight that arrives in the vicinity of a MEER, and there's about 10 to 20% reduction. And if we look at, let's just skipping ahead and come back later, in terms of cooling, we can achieve at 10 centimeter depth in soil up to 3 to 4 degrees Celsius of cooling, even in not so sunny New Hampshire. And we expect that in many parts of the US, we can achieve up to 10 to 15 degrees cooling at about 10 centimeter depth, where there's more abundant sunlight. And that would certainly safeguard our crops. And we're currently doing experiments to look at moisture retention using the same method. So with that, I'd like to handle it back and take questions.
Thank you so